Good afternoon, Byron, Benson, Bekaert Corporation. I'm here to talk about a design model. We've heard a lot of really good research. This is going to shift gears a little bit. We're looking for something practical. We want to use what's already out there. We're not looking for anything new. We're not looking to change. We're not looking to validate. We're not looking to create anything new or suggest changes to any code, but to use what's out there for the actual design of slabs on grade. So we did a comparison. There's some research that's out there. You can see these tests here. This is research that we used to develop this model. We didn't use all of them, but we chose among this research to present and develop our own method. It's based on the 2010 approach for uncracked concrete, and then we also, after the concrete cracks, then we switch models. I'll get to that here in a minute. But this methodology assumes uncracked first, goes through, can predict the number of cycles in conjunction with a certain stress level to the first fatigue crack. And then after the concrete cracks, then we switch models, and then we can predict the total number of cycles at given service levels, or inversely, service levels given a number of required cycles for the slab on grade. So you can see it's based on this one here primarily, and then our own lab tests. It's also backed up by some full-scale tests. This is, as I say, I forgot this thing did these transitions. Yeah. So yeah, as I said before, we have the model code 2010 approach for before cracking, and the equation that we used, it'll look very familiar because we saw it before. The stress ratio that I'm talking about is the applied stress over the static capacity stress, and the 2010 model code equation is that line there. This is the one that we use. That one there should look very familiar. That's the one that we saw before. So given any number of required cycles, we can determine the maximum stress that can be applied at each cycle to achieve those numbers of cycles, or given a stress, an in-service stress, we can predict the number of cycles that element can resist at that level of stress. This is one set of testing that we did. It's based on a beam test. This is the protocol that we followed. This follows the EN 14651 beam test. This is the pre-cracked section. This is the pre-cracked specimen that we looked at. One fiber type, the 3D 8060 BG, concrete mix, but different dosages of that fiber and at different stress levels. We also adopted the FR1. So everything that we do, our SR is a percentage of FR1. The results of the beam test, you can see here at the higher percent of FR1, you can see clear differences between the different dosages at higher levels of stress, but you can see at lower levels of stress, they tend to converge at this lower level at higher load repetitions. The University of New South Wales, they did several series of tests. We used the panel results in our tests. We found that the panels behave better under fatigue than the beams do. Bigger specimens perform better than smaller specimens, and the total crack area of the panel is quite a bit larger than that you get out of a standard beam. So these are the series of tests and fibers. These are Dramix fibers, 5D and 4D. This is the aspect ratio, and that's the length. And the BG, the B is bright, and the G means glued. Our fibers all come in glued strips that are about an inch and a half wide to help prevent balling. That's the dosage, 30 kilograms. there's the concrete, and that's the specimen size of the round panel. I don't know what was tested at 180 days. I never got an answer for that. Just these are the numbers of tests, max loads, static, fatigue cracked, pre-cracked. We also looked at one pre-cracked specimen as well, which is just informative. Yeah, there it is. There's the area of the panel is 5 times the surface area of the beam. So it gives better results. So this is the result of the University of New South Wales. This is after cracking. So after cracking, this is the curve fit. This is the equation that we get. So again, based on the number of cycles that you want, we can predict the amount of stress per cycle to live to those number of cycles, or conversely, given a stress level, we can predict the number of cycles that section can carry at each cycle. This is a really good curve fit, but this is also the standard. More tests are needed to validate this. But this is evidence, and we heard before, 2010 says do the testing and make the case for it. That's what this is doing. We're making the case for fibers in the slab. This is a very good curve fit, and it predicts very, very well. There are some examples later, but it fits very well. So going along the same lines of we are doing testing to show that this is a viable solution and a predictable solution, and the results are good and consistent. This is also backed up by some large scale, I think I said full scale before, but large scale tests. We did these specimens with this setup. I know this is kind of small and you can't even read that, but that's 1 meter wide and this is 3 meters long, and I think that's this span here between the loads. But this is the table of the loading for that large scale test. This was done specifically to verify and to justify for justification for the round determinant panel tests. These are the parameters that we tested here. So trying to mimic at least something realistic as far as the slab is concerned. Now, keep in mind, this is specifically for slabs on grade. It's for no seismic loading. It's for wheel loads, no uplift loads. It's not for slabs on piles. It's just for uniformly supported slabs on grade under the action of wheel loads. So this is, in words, the way we approached it. We have one model to cover the fatigue behavior at the first crack. So we start with uncracked concrete and determine at what point does it crack from fatigue, not from load. When does it crack from fatigue? Then the second model takes over from that point to the final life of the element. So yeah, there's in words there. Fatigue performance of larger specimens is better than smaller specimens. Slabs have better performance than round determinant panels. Round determinant panels have better fatigue performance than beams. So there's a progression up to our large scale test of slabs. So as with most things concrete, there's lots of parameters, there's lots of scatter, but what we're trying to do is to find something that's relatively simple. What can we do that is not overly cumbersome but still produce repeatable results that's backed up by research? So again is UNSW, just some verbiage backed up by large-scale testing. There's limited number of tests. Obviously, there's practicalities with cost and time, but the results are reasonable and in line with practical experiences, in line with what we expect. Most specimens took all the testing in terms of cycles that we did, most specimens took the cycles without exceeding the fatigue strength. So very, very good performance out of the fiber concrete. In using this model, when we started looking at this, I was among some of the folks at Bekaert to say, why are we doing this? We've been putting slabs on ground for 40 years. We don't have any, to date, no fatigue failures, no fatigue concerns or even problems at all. Why are we doing this? Well, part of the reason is because our customers are starting to ask for it. More and more our customers are asking for it. So we're just really kind of looking for how can we address the concerns of our customers, but then also how do we mitigate this? This is a complicated topic. There's not a lot of data out there. There's data showing that fibers do help concrete perform better under fatigue, but there's been no real practical application for them for slabs on ground. So we say, okay, it's complicated. This is kind of new. There's not a whole lot of information out there. So that's why we're going to limit to just simply ground-supported pavement slabs. There's a minimum dosage that has to be used in the slab no matter what. But then also, we go back to, we've got decades of experience of putting and designing slabs on grade on various different uses, many different uses from ports to warehouses, and no concerns whatsoever of fatigue performance in any of them. So but it's still a means of addressing our customers' concerns because they are asking it for fatigue design or fatigue performance more and more. So how do we do this? We have our own proprietary internal software that a number of things that we can design, but our bread and butter is the slab on ground. Straightforward implementation. We can handle wheel loads. We can handle joints. We can put loads near joints at corners in the field. Various magnitudes, various numbers of wheel loadings, magnitudes of wheel loadings. So we said, well, can we find something that we can reasonably easily incorporate into this existing slab on ground tool that we already have? The answer is yes, we can. It's based on a yield line approach, plastic design, but in the yield line approach, which is very common. And we think that we can just simply incorporate a simplified version of fatigue into this model. What's next? Well, the topic of FEA or FEM came up, and that could very well be the future. There's lots of talk about let's start incorporating finite elements into our designs, but we're not going with this yet because we're not designers. We're manufacturers. So we recognize the FEA models that we have. The ones that we have access to, they don't have the ability to track cracking and to modify the loading as the moment of inertia changes with cracking. So this is something that we want to do. We want to move into that, but as it is right now, it's the more simplified yield line approach that uses a modified load factor approach. Yeah, again, so here's the applicability of the scope I've already mentioned, strictly to ground-supported industrial floor slabs and pavement, downward forces only, wheel loads, minimum 10 to the 4, maximum 10 to the 7th, load repetitions, and right now this is to a certain level of use within Bekaert while we're still developing it and figuring out how to make it better, how to extend it, that sort of thing. These are the fibers that we have that we would use for slabs on grade and that we would use for this methodology. Minimum dosage of 30, which was mentioned before, and the concrete is between C25 and C40 or 35 to 6,000 concrete, which is going to cover practically any slab that's out there. So how would we do this? So this is everyday design. The applied loads, you applied your load factors to it, you get a moment. You have your material, you have your resistance factor, you have a design capacity. But the resisting capacity and the moments, they're related by the load factor and the resistance factors. Similar thing for fatigue loads. We have the loads, the load factors going into a design moments. We start with the resisting capacity. We can reduce them by the stress ratio that's in the research. And then we also have a fatigue factor that we come to a long-term design capacity considering the stress ratio and the fatigue. And these two are, again, related by the stress ratio and a fatigue factor. This is, we'll see later, this is a safety factor that built in that if it's desired to have a larger factor of safety on fatigue, then we can do that. But as it is, our wheel loads already include the 1.2 impact factor, and we consider fatigue as more of a service level. So our fatigue factor is 1.0. Using this idea, this methodology, we said, well, can we just simply equate this to that and come up with a new material factor that we can simply incorporate into our model with a new factor for fatigue, considering this methodology here. This is what we came up with. So we take the design factors for fatigue and convert them to an equivalent material safety factor. So we've defined internally a new equivalent fatigue factor based on the load factors and the fatigue factors for fatigue. This is for static. So we call it Y prime or gamma prime of the material. And so these are the load and resistance factors equal to this. You can see that equivalency here. These guys here, I just simply inverted it because the 1 over complicated thing. So both of them are inverted from that slide. So there's no 1 over here. But this is also inverted. So you solve that, you have this material factor is the fatigue over the load and the stress ratio factor. So we take the larger of those. The final design also includes serviceability and ultimate limit states, but this is just yet another check. The larger of the above factor and the static material safety factor is applied for each material in order to derive the moment capacity M prime of the system. So then that moment capacity is then applied, obviously, to the wheel load moments that are determined by the design tool. This looks very complicated, but you can see the equation here, gamma factor, load, that's each one of these. This is obviously the European methodology. We have the partial safety and reduction factors that they apply to the material and to the different uses as opposed to the way we do it here. But this is what is incorporated into our internal design tool as equivalent safety factors specifically for the case of fatigue. The fatigue capacity of the system calculated as a multiple of the first crack moment, and I'll show that in numbers here in a bit. But it's this phi factor for fatigue, the maximum. Here you can see, say, the stress ratio for uncracked and stress ratio for cracked at FR1. There's our FR1. There's our first crack strengths here, and this one here is for FR1, and this is cracked. And we use a large of those. These are the definitions. This is the equation that we saw before. That's the equation for cracked, and N is the number of cycles. That gets plugged into this equation for the moment capacity of the system under fatigue loads by this equation here, stress times section modulus times the factor for fatigue. That's how we incorporate it into our model. We're able to plug this directly into the equation in the model that we already have and have been using for years. As I said earlier, an optional safety factor fatigue, we can incorporate that if that is desired. These are the results of the large scale test, the slab that I mentioned before. So I'll isolate this one here in a moment and kind of run through 3 million cycles. This means that we ran the test to 3 million cycles and then stopped after 3 million cycles, but the section did not exceed its capacity. So based on this test, thickness, this one wasn't pre-cracked. There's one that was pre-cracked, but this one was not. Fiber dosage, minimum loading, maximum load. This is FFL, and this is FR1, and repetitions until first crack, and then the maximum repetitions. So I'll show you how that is used with the methodology. This looks a little complicated, but it's really not. So here's the number of repetitions until first crack. So you take that 1796, you plug it into that equation, and you get this stress ratio of 73%. Then you can take this maximum number of repetitions, you plug it into this equation for the cracked the cracked concrete, the equation for cracked, and you get 65% stress rating. Now you take those numbers, the FFL that we had before, times this stress ratio FR1, take all of these numbers, plug them in, what pops out is 119%. Then you take the force at the first crack, multiply that times 1.19, and you get that our predicted maximum capacity, for a given number, maximum F predict for given numbers of cycles is 310 kips, or kilonewtons, sorry, this is all European. Well, but what we saw applied in the test was 343, so that's 90%. So this model predicts that particular specimen predicted at 90% the maximum number of cycles that section would be able to carry at these given intermediate stress levels. You can see here that it's not bad. Some of these are a little, but 90, we're hovering right around 90, 100%. Good overall predictability of the model. Keep in mind it's simplified and trying to be practical. If we take that methodology, incorporate that into our tool, doing this sort of example, 800 kilonewtons, that's 180 kips of load, wheel load, using the Bekaert approach. Again, this is a European methodology. Our tool can also design according to US methodology, but this is the Bekaert methodology uses FR3. US methodology uses FR4. Soil parameters and 5 million load repetitions. There's a checkbox in our tool. I'm not showing that here, but there's a simple checkbox in our tool that we can incorporate the fatigue into the analysis. But here's the input. There's the load factor. Here's the wheel impact factor that I mentioned before, the 1.2, the fatigue factor of 1.0. And again, these are the European, the partial reduction factors, material reduction factors that are used. This is the static, that's the fatigue. The tool looks obviously at static, ultimate, and fatigue, and the most critical governs. So these were the parameters that are used in this particular example. This is the dosage, that's the concrete, and there is our slab thickness that we recommend for this particular use to carry all serviceability, ultimate, and this fatigue life at that level of loading per cycle.